to join our room, please take a moment and think about who we should consider for speakers in our spring and fall quarter. This is your research seminar, so we welcome cross-disciplinary speakers, network science, complex systems, computer science across anthropology, biology, computer science, data science, economics. Please make this a very interdisciplinary series, as it always has been, and we genuinely request input from our participants. So thank you for considering and putting any ideas that you have in the chat, where Andy has added a link to suggest a speaker. We have a couple of announcements before we welcome our speaker. Data Science Nights is coming up on Monday, February 28th at 5:15, where we are happy to welcome Emily Weber from Amazon Web Services. She will be talking about a day in the life of the Amazon SageMaker team. Please join, and particularly, we'd like to extend an invitation to any students students of any level who are interested in taking a greater leadership role in our data science series. There will be a discussion after Emily's talk about how you might be able to get involved. There's lots of exciting things that can be done, so we really welcome your participation. And also next week, Melanie Mitchell from the Santa Fe Institute will be doing a talk at the Northwestern Cognitive Science Colloquium. So Melanie, as many people know, is from the Santa Fe Institute and is a great luminary in artificial intelligence. So please join that talk if you are free and interested. With that, I would like to share just a few reminders. Our speaker would be happy to entertain questions during her talk. If you could please put any questions during the talk in the Q&A. And at the end of our talk, there will be also time for question and answer. If you'd like to ask your question live, please hit the raise hand button and we will unmute you so that you can ask our speaker directly what your questions are. With that, the talk will last about 40 minutes with Q&A at the end. I would like to introduce one of our NICO core faculty, Danny Abrams, who's a professor of engineering sciences and applied mathematics. Danny will be moderating and introducing our exciting speaker today. Thank you so much, Danny.
Thank you, Alana. So I'll try to keep the introduction brief just because I want to give Staša maximum amount of time to talk, but our speaker today is Staša Milojević. She's broadcasting to us here from the Luddy School of Informatics, Computing and Engineering at Indiana University Bloomington. She's got a really interesting background. I was talking to her earlier about this, that I think is quite unusual for someone with her scientific interests. Her undergraduate degree was in English language and literature, though she tells me is more like philology, a bit of somewhat quantitative, maybe more in the direction of linguistics. But then she moved into informatics for her master's and PhD from UCLA, and or master's from Kent State. Sorry about that. But then anyway, since she moved into research career, she's done a wide range of interesting work mostly on the science of science, but also related areas. And she's had some amazing, really interesting publications in major journals in science, in PNAS, the Proceedings of the National Academy of Sciences, and in Scientometrics, lots of major journals, but also in Nature Reviews Physics, in Physical Review Letters, premier journals for physics. I think she's one of the few people with a degree in English that has published in Physical Review Letters. So I think that's really interesting. And in general, I think her work is super interesting. So I'm looking forward to hear what she has to tell us today. So I'll give you the floor now, Staša.
Thank you, Danny, for that introduction. And let me start sharing the screen. And that's really interesting catch. I think most people don't go into the background to that level and are not aware that I'm not a physicist. For some reason, most people think that I have background in physics, but I do not. So it's a great pleasure, actually, to talk to this audience again. NICO is one of my, and Northwestern in general is one of my favorite places because it does have a really high concentration of people whose work I really admire the most. And it's really always exciting to have a chance to talk to people at Northwestern. As Danny said, my research mostly is in the area of science or science studies. And I did spend quite a few years now, over a decade, developing different topics in this area. So what I want to do today is really give an overview of maybe what the major theme, like bringing together what I was doing so far is, and that is the changes that contemporary science is undergoing. I used to call this kind of combination of topics, changing landscape of knowledge production. But after one talk, I had a pleasure of talking to Paula Stefan, economist of science. And she said, well, what you're talking about is tectonic shifts. And I like that better. So I switched the title to tectonic shifts. So there you go. When you think about this changing landscape, and let me minimize the window, sorry. So when one thinks about this changing landscape of knowledge production, one could say that science in general has been changing throughout its existence. But really, some of the major changes that we are still experiencing today are the result of post-World War II world and the way science started developing after that. These dramatic changes in knowledge productions are exemplified by a lot of things, but for this particular talk, I want to focus on three particular aspects of science, both individually, but also they interact. So the first one is increased pressures on productivity. I don't have to talk to any of you about that. We are way beyond publish or perish world, but it is still very real pressures on simply productivity, but actually now combined with calls for impact. Then there is this push towards or idea that we need more interdisciplinarity. So we are experiences both funding and administrative push towards interdisciplinarity. And finally, we have this shift towards more from individual to team science. So let's start with this push towards publishing more. That results in pure growth in publications. And again, for any of you who were following the science of science literature or scientometrics literature, growth in publications is something that has been observed going back to the 1960s. And this is just an illustration. So in the field of astronomy, we are back in 1960, there was one paper per day, but in the early 2000s, 20 papers per day. If any of you on AstroPH archive these days, I think it's close to 100 papers per day. So very, very significant changes in just the pure number of publications. If one wants to take a look at the growth of publications overall, this is what it looks like in Web of Science. So Web of Science is selective, right? This is not everything that researchers and scientists were collectively publishing, and yet we can see significant increases. And if we look at the number of research articles that are being published, we do see the exponential growth, and we do see that the doubling time has been changing, right? So it's been exponential, but not at the same rate throughout the period. After a relative slowdown from mid-70s to mid-2000s, we are now experiencing again a slighter uptake. So if you look at this, and if you are living through this deluge in a way of papers, you might be wondering, why would anybody ask the question, is there a slowdown in science? And if so, why? And actually, this is a real question. I've been encountering it a few times myself. And in a way, it may be puzzling because it does not seem that the science is slowing down. This question came up in the recent OECD workshop on artificial intelligence and science, where there was this notion that science is slowing down, and can we use artificial intelligence to kind of jumpstart it, right? Or give it a new push. In the most recent Wong and Barabashi book on Science of Science, they do have a chapter which actually has the same question. So it is a legitimate question. So why this feel that science is slowing down? And is it something that's really new, or is it something that is relevant in the current moment? And the question is not. So if we go back to a world of science right after World War II, science really was the major hero of World War II. It saved lives, it shortened the war. So there were major advances in lots of the areas, like from medical interventions to the computers. And this that success of science was really captured or utilized by Vannevar Bush, who was behind Manhattan Project, who was really instrumental in a lot of the physicists' effort in World War II. But he actually stayed in science policy circles after the war, and he spearheaded two things. One is this report called Science, the Endless Frontier. And even if you are not in science policy, you might have heard the expression, and he was behind the report. And the idea is that he firmly believed that science is equally, if not more important, in the development of any society, its economic and general well-being, but that science, in order to achieve its potential, needs support, and that it needs such a support from the government, but in a way that science is still autonomous, right? That scientists are the ones who decide on what they're going to work on. So it's this, and that's what we have more or less in another thing that came out of his effort, which is National Science Foundation. So he was behind founding National Science Foundation. And these two things, more autonomy of science and this extensive government funding behind science effort, is really what Vannevar Bush is behind. And there was this sentiment, right, that science is the endless frontier. There was a lot of resources poured into science, increases both in the enrollments in universities, but also in funding for research. And that really makes it strange that even early on, right? So this is happening post-World War II, like in the 50s, we see the foundation of these institutions. But actually, it's already in 1961 that we have one of the founders of Science of Science, Derek de Solla Price, really notice the idea that this exponential growth that everybody was so excited about is really not sustainable. So if one thinks about science as a closed system, because it does have limited resources, especially when it comes to the human power. So what Derek de Solla did, he modeled. So he said, well, what looks now an exponential growth is not sustainable. If it is sustainable, and it had that quote that if we continue in this route in, I don't think, 10 years, every man, woman, child, and dog would be a scientist. And we know that that's not going to happen. So based on that, he actually said, well, it's more logistic growth. So, and that means that science will reach a saturation point. And if science reaches saturation point, it will slow down. And the question was, when would that happen? Everybody was hoping, well, it will happen sometime in the future, but he suggested that actually at that time, science has already entered that phase. And like panic is maybe too strong of a word for people who are not in science of science, but it actually prompted a very extensive discussions, especially in the funding and science administration circles. How can we prevent that? Like, how can we keep science growing and advancing? For people living in that period, it might have seemed unique, the way it may seem unique to some of us living in another panic mode of that sort. But actually, it's not new. I came across this really interesting fact that back in 30s, or that Charles Babbage wrote the Reflections on the Decline of Science in England, right? So he had the same thing, saying, well, science is experiencing decline. And he's the first I found. He's the first in the long line of people who were raising, and there were French scientists who raised similar points a few years after he did. And there is this long line of scientists who are not satisfied either with the stature of science in their own country, France or England in this instance, or the particular discipline vis-a-vis other disciplines. So in lots of these early calls of declines of science in England and France, the comparison was between chemistry and state of chemistry in these countries and what is now Germany. And again, a lot of these calls are really calls for generating support and getting support for further funding in science. So going back to it's historical, right? Like this moment is not new. People have gone through that multiple times. But what is new is our answering the question, is science in decline or not? And how can we know, right? If we use papers, it's growing and it's growing exponentially. If we use number of people, it's really super healthy in terms of it's really growing exponentially. But then I was really wondering, and that was back now almost 8 or 9 years ago, but what would that even mean? And what does that mean for how we define science? So if science really is researchers, right, we should measure number of people, and that's okay. If science is about publication, and if publications equal knowledge, so if science is about knowledge, and it is, one way to measure that is through papers, but then we can question, is a paper a good unit to measure unit of knowledge? So usual measures that pertain to progress of science are related to volume. So I've talked about number of papers, which is productivity, and number of researchers. And if you use those measures, you can compare countries and say, well, science has fewer papers than Germany, which has fewer papers than the US. And people still measure that, and I'll show you some of the results. Then there was this notion, but just writing papers is not enough. Not all papers are equal. Some are more impactful than the others. So there was a shift towards looking into impact, which was the number of citations. And while that may get us closer to what may contribute to advancement of science, there is still an issue of volume, right? Because small institute with fewer papers but higher number of citations per paper would seem to be producing more knowledge, quote unquote. So impact itself is also not a breadth of knowledge, right? It's not how much of how much of the territory of unknown science is covering. So I was wondering for a while, is there a particular measure that we can develop that would get closer to trying to measure science as knowledge? And I got this idea that if we can think of science as a territory, right, that it's covered, it's a cognitive territory, how much of that territory is being occupied in any given moment in time? So, and the idea is, can we find a measure that would be independent of volume and that could be then equally applied to time periods in science areas and countries over time? So I then worked on developing a statistical measure for method for measuring what I call the extent of the cognitive territory of scientific literature. And it was based by using some of the natural language processing techniques where I was extracting concepts by parsing titles into phrases. And again, we can talk about what is a concept, but in general, it was phrases of different length. So this method allows for keeping concepts of different lengths, from single words to up to 7-word phrases. And in order for this to work, you need an unbiased sampling of the cognitive territory, which uses the same number of articles or similar number of words. And then what you do with that, you count the fraction of unique phrases, right? Because each phrase is occupying part of the territory, so small fraction of unique phrases in particular body of work means that there's a lot of repetition, right? People are working on similar concepts and that they cover small territory. They can write a lot of papers, and you can think about that they're drilling a hole, right? They're getting deeper. Another possible outcome is you have a high fraction of unique phrases, which means that you cover a wider range of concepts, which means that you cover a larger territory. Depending on number of people you have, that may mean that you are more just exploring and not solving. But if you have a lot of people, you can actually be going both deep and wide. So for this is a statistical measure, and you need a large measurement quota to reduce the stochasticity that is present in individual titles. So I already mentioned that you can use this to follow how things are working over time. So I applied it to see how fast science is expanding, or is it expanding at all? And here are the results. So at the top here, you see the same plot that I've shown you early on in the talk, where you see the exponential growth, which is not only the same. When we apply this measure of the cognitive extent, we get a different view. We see that actually science grows more linearly and not exponentially, which is closer to the intuition we may have of how science develops. We can also see two very interesting periods, or actually three. We see that the periods of largest expansion in terms of science are right after World War II, and right from 58 to 65. And after that, we have some expansion, and what may look somewhat worrisome to some, and that may be worrisome long term. I don't think necessarily short term it's a problem, that in the mid 2000s, we have entered the period of relative stagnation and even decline in the number of topics we have. This particular plot is interesting because if you look at the exponential growth of the publications, you do see that the limits, right? You see that it starts like that period of quickest expansion starts at more or less the same time, but actually when it ends is somewhat prolonged in the number of papers. Oops. What is interesting with this one is I've recently heard, and that is discouraging, that science experienced highest increase right after wars. So somebody said we needed another war to see the increase in science. I hope not. But in general, this sort could support that. This is the actual war, and this is Sputnik and Cold War that we are seeing that. So why is this important, and why people pay attention to this? It has to do with funding, because scientists themselves use this to argue for more funding, and countries who want to compete also look into how they can increase development based on funding. So this here shows you the funding in billions of 2020 US dollars, and we do see that more or less there has been an increase. Although if you translate that to the percentage of GDP, there was a decline in the funding. But in general, in the absolute numbers, there has been increase in funding science. But if you look at the cognitive territory in the United States, you can see the actual decline. So you can see that researchers producing work in the United States are covering smaller and smaller territory, meaning they are working on smaller number of different topics. Science is really driven by fields, right? You need these larger units where all of this knowledge creation is happening. So fields or research areas are very important for that. And here I show you the difference in two. So this is physics and medicine. So in physics, we see that physics has experienced consistent expansion of the cognitive territory over time. Whereas in medicine, we see some growth, but very moderate growth. And then actually since 2000s, we start seeing the decline in medical research. Interestingly, funding for physics has stayed flat for a very long time, for 50 years, whereas funding for medicine has experienced significant growth. I looked at the different fields and the factor increase in funding and factor increase in cognitive science. And these are some very interesting results, or at least I find them interesting. If you look into funding, you can see that, and like the data shows that the biggest increase in funding was actually in computer science. And what is interesting is that although computer science, yes, they received a lot of funding, but they actually significantly expanded their cognitive territory, right? They expanded the number of topics that they are working on, the number of concepts that they are dealing with. astronomy seems to be, they can argue, hey, you didn't give us that much money, but we did awesome, right? We are expanding, and they are. If anybody follows current astronomy with the multi-wavelength astronomy, they're doing phenomenal things that are really close to physics and merging with physics in a lot of ways, and like serving as more experiments for experimental sites for particle physics. But so medicine, however, has received significant increase in funding, but is the field that expanded the least. As I said, this is type of stuff that a funding agency and science policymaker at the national level care about. And a reason for that is this competitiveness. All the science is universal based on Merton, so we do share results globally. Science is also competitive, right? So we are in a strange moment where we collaborate, but we also compete all the time. And countries really follow how they fare compared to other countries when it comes to science. I mentioned the publication volume as one of the measures, and it has been closely followed. And US was the leader for decades, but it has been surpassed by China. This is the 2019 data. So China now is the biggest producer of papers on planet. But if you look at the cognitive extent, you get a slightly different picture. So US is still covering larger territories. So US scientists are still working on more concepts or different concepts than their Chinese counterparts are. But the countries that have much less of a productivity have larger territories. So they are not having as much repetition, but they seem to have lots of one-off papers on a very large number of topics. So this is what the cognitive extent map looks like. If you look at individual research areas and compare where different regions like United States, European Union, and China stand, you can see that in lots of these areas, US or, well, actually in all of the areas, the lead is either by US or EU or European Union, but China is really catching up in three areas: in engineering, in physics, and then medicine and computers. And again, there is another research that shows, in a way, hi.
Interrupt, sorry, just for a second, because there was a question that I thought you might want to address at this point. And the question is, how do we know that the apparent reduction in cognitive extent represents an actual reduction as opposed to an agreement within fields to use a common vocabulary or coercion from funders to do that?
Like, I think you're absolutely right. I think it's there is a lot of agreement. So, but it also shows you. So again, if we think, and that's where I say this may be problematic long term. I think what you mentioned short term is absolutely right. And like there has been a long line of research that certain fields that advance more are the ones who coalesce around common language or common problems. And those are like, and we know that historically physics is one of those sciences where there is a consensus and there is more or less agreed upon vocabulary, and they are able to form research front and move it forward. In other fields, especially social sciences, there is not agreement on the vocabulary, but also other reasons, fewer people working on moving and no research front. However, future ideas, if you think about long term, like we should have a good number of new concepts coming in, some of which would be fruitful enough and would be the ones that the community will choose in the future to focus on and solve. So I think what is happening probably in the moment, and this cannot be answered by this, and it's a great question. I think that in a lot of countries, we may be seeing this coalescing and solving existing problems because we agree on what they are, and maybe, just maybe, not producing. And lots of these ideas are crazy. They're never going to be picked up, like they just appeared, but we may be actually slowing down collectively as producing these new topics that some of them will be picked and people would coalesce around. But that's a great question. I hope it answers the question.
Thanks.
Okay. So I want to move to the second thing that I mentioned, which is interdisciplinarity. And there are different ways that one can operationalize interdisciplinarity. What I did, and this is the research that's actually a result of two separate lines of work. One is the work I did with Filippo Radicchi at IU and John Walsh from Georgia Tech, and the work that I'm currently developing with Bruce Weinberg from Ohio State, and Drew Hanks from Ohio State, and Kevin Kniff from Cornell. But the idea is, again, there are increased calls for a need for interdisciplinarity, and it's understandable if one goes to the models of science, such as mode 2 development of science. The idea is that the problems society is facing now are so large, right? It's these grand challenge types of problems that really need people with very different types of skills and data to work together in order to solve those problems. Like, we cannot stay in silos and solve these problems. So there was this push of increasing interdisciplinarity. I think the measures of interdisciplinarity are based on two things. One is what you measure. And for these projects, we decided to focus on measuring the knowledge base, right? It's how diverse is the knowledge that these papers or teams or authors or fields are drawing from in the work they produce, and that's based on interdisciplinary composition of the references. You can have the interdisciplinarity of citation, which is this work really was such in nature that it must have been interdisciplinary because it affected lots of different fields. And then there is the third line, it's really, I won't say equates, but in a way it equates interdisciplinarity and team science, where you do have to have teams with different sets of skills to call something interdisciplinary research. So we are based on references, and we are also based on this idea, which is similar to mode 2, that in order to call something interdisciplinary, it needs to be from very different areas. So not two subfields of physics, but really physics and sociology, or physics and biology. So these are the premises. If we computed the interdisciplinarity or average interdisciplinarity for these broad areas that you can see below, and there are two things. If you look at what the average interdisciplinarity is, it's very low. It's much lower than most people would expect. But the people or the areas that engage in less interdisciplinarity are our usual suspects, right? Humanities, mathematics, and astronomy. Areas where we see the largest draw from different fields are agriculture, psychology, and biology. Again, probably is expected. This is the distribution of interdisciplinarity across the fields, and this shows what I told you, which is, so despite all of these calls for interdisciplinarity, especially funding calls, there seem to be strong incentives to engage in interdisciplinary research. And yet, based on this, it shows that majority of papers that are produced really draw from knowledge from a single literature. And then we see increase, but most of the time that doesn't go like very much beyond 60% of interdisciplinarity. When one looks at the changes in interdisciplinarity over time, good news is when the interdisciplinary research that is being produced is more interdisciplinary than one before. So there is definitely an increase in the average interdisciplinarity in the work that's produced, but still a very small fraction of papers are truly interdisciplinary in the nature. So a lot of what we do is still fairly siloed or fairly focused. This led to the line of research. And so this is the research that I mentioned that I did with Filippo and John. And I'm going to show you some of the results of the work that I'm working on currently with Bruce Weinberg and Enrico Berkes, and that's the demand and supply of interdisciplinarity in biomedical research. So the stuff that I show you included a whole web of science in all of the fields, and here we look only at the PubMed literature. We use the same measure of interdisciplinarity, which is the fraction of interdisciplinary references. And here I show you the increase, and then the idea behind this is, if interdisciplinarity is so good, right? Why is the scarcity, right? Like based on economics, everybody would want to do it because there should be a payoff, right? It seems to be something that's desirable, and yet there are still calls that we don't have enough of it. And that's the type of thing that we are trying to address here. Why we don't see much of that? And maybe is it a type of like supply and demand sort of thing? So here at the top line, we showed interdisciplinarity by year, and we see that it's increasing. And here is the level of interdisciplinarity in terms of publication for incoming researchers at their graduation. So we do see that, of course, these two follow each other, as you would expect. But and the difference is very small, but it's statistically significant. But what is really interesting, that the interdisciplinarity that we are seeing is not driven by these newcomers to the field, but in a way more established researchers. Although, if we look at the advisor-advisee dynamics when it comes to interdisciplinarity, it does seem there is a strong correlation. So on the x-axis, we have average or median interdisciplinarity of advisors 3 years prior to advisees joining their labs. And then we have initial interdisciplinarity of their advisees, and we do see very strong correlations. So students or advisees who tend to join labs or who tend to work with highly interdisciplinary advisors tend to also produce more interdisciplinary research themselves. However, interdisciplinarity is risky, and it may explain why we have lack in supply. So we divided all of the incoming researchers into the quartiles of how interdisciplinary their research is. So quartile 1, which is this line at the bottom, is the least interdisciplinary research, and quartile 4 is 25 top researchers in terms of the interdisciplinarity. And we looked at the attrition. It is interesting that students or researchers who enter, whose work is most interdisciplinary, have highest attrition rates, and that receives, like, it peaks at years 7.5 to 10 of their career, which may actually correspond to when the tenure decisions are made. But this also shows that doing interdisciplinary research indeed is risky, and we do see that the least interdisciplinary research have a least threat of having their research careers shorten, or at least their publication research career shorter. And again, this could be just the fact that if you look at the jobs ads at all, most of the job ads are more in the past, right? The well-established area, and not so many at these things that are very difficult sometimes to pinpoint, because this research in general is more novel, as was shown by research done by Uzi and other people at Northwestern. We looked then, and this is preliminary, we divided people into above and below median for their interdisciplinarity and follow their interdisciplinarity over their careers. And it's really interesting that this increase in interdisciplinarity is achieved. So the high, like, people with the highest level of interdisciplinarity are at peril, and they leave a field after 7 to 5 years. But what happens around 10 years, people who were not so interdisciplinary have significantly increased the level of interdisciplinarity, and they're much closer in the way they do their work to the people who were highly interdisciplinary. So we do see that people who started highly interdisciplinary lowered a little bit the level of interdisciplinarity and stayed more or less stable, but we see significant steady increases in the levels of interdisciplinarity. And I want to move to the last topic, which is the science as a team effort. And I want to cover one particular area of interest, which is big science, which is usually tied to this world after World War II effort, and some of the stuff from the late 30s, like the cyclotron at the University of California and the Manhattan Project and Apollo. Interestingly, and that may be relevant, the first true big science project was in philology, and it was in the Corpus Inscriptionum Latinarum. So it was the Prussian Academy funded this project of collecting all of the Latin inscriptions. But the project was so big, it lasted longer than any career could have lasted of any individual researcher. And it was so massive that it needed state backing. So actually the first big science project was in humanities or in philology. The next big one was also at the end of the 19th century. It was astronomy. It was spearheaded by France, but it included 36 countries. And it was this map of the sky project, which ended only in the 1960s. It was a massive project of like collecting all of the photos from or data from observations from a very large number of observatories across the world. When we think about big science today, we think about, as I say, physics, astronomy, and biology. So this is the research that I did with Kati Borner and Felipe Silva, where we visualized six big science projects in these three areas: physics, astrophysics, and bioscience. And we got something interesting. So most of us, when we think about big science, we think that big science starts big, but actually big science starts small. It starts with a handful of enthusiasts. It starts with a few, and this is for LIGO, which is one of the largest. Actually, Atlas is still the largest, but this is really getting close in terms of how many people. So you see, this is LIGO when it started. Only 3 institutions. And we looked over time how it developed, and you can see the quantitative jump. And so over the years, this is what LIGO looks like, and this is now. So this is relevant because a lot of research, again, some from the Northwestern, shows that not only that the team science is more of a norm, but big science project is also more of a norm, right? So it's not only that individual researchers are more or less thing of a past, but the teams we have are getting larger. And I think it's important to try and understand their nature, like how they form and what are their characteristics. I don't think they're just bigger, right? I don't think it's just simple scaling. I think they are different in nature. And I think it's something that one goes back to the 60s and the term big science when again, Price and Weinberg, when they introduced it, they also pointed out that these projects are inherently different. And I think personally that we should try and understand more how this works. And this cannot be analyzed, at least not collaboration-wise, with the data we have or metadata from the publication. So we need other data sources for that. It raises the question, well, are then small teams things of past? Like, do we need them in the big science era? So going back to that cognitive extent measure, I show you here the cognitive extent in physics, astronomy, and biomedicine. And you can see that very large teams, which are ones at the bottom, cover only a fraction of everything that's done in these fields. So, and I tested it, and not only that, but all of the topics that are covered by the largest teams are also, they don't have any unique topic. All of these topics are covered with this, like by the work of the small teams. There is also this inverse correlation between the team size and the cognitive extent. So in physics and astronomy, the largest cognitive territory is covered by single authors or like very small, up to 3 person teams. In biomedicine, it's 3 to 5 authors, but it's the nature, it's the lab-driven work, so it's expected. And that goes back to that excellent question, which is, if we want to think about the future, right? One thing is that these very large teams, which are being pushed, like a lot of the calls are for these large efforts. And there is a work that was done by Dashun and James Evans that also tells us that small teams are, I think they say they are disruptive, right? And big teams are solving. And here it shows you that all of the new concepts are pretty much introduced first by small teams. They get picked up by big teams and they get solved and developed. You need big teams for that. But small teams really seem to still be seeds of the ideas. If you look at the interdisciplinarity and team sizes, in certain fields, the findings that the more interdisciplinary the team, or the larger the team, it would be more interdisciplinary. And that is true for a lot of the fields, but we're seeing something interesting here, that is definitely not true for physics and astronomy and even biomedicine. So I think it's really, again, it's an area where it might be useful to look a bit closer what is happening and how. And I want to conclude with another role that teams play, which is citations. So again, for all of us in academia, impact and citations are important. There was a lot of research on citation dynamics, how we get citations and model of that. So here I follow the evolution of citation distribution of close to 6,500 articles in astronomy published in 2007 to see how to look at their citation dynamics. And some of the models, so the model of this dynamic is the best known model, citation distribution model, is the Price model, which implicitly combines, so the idea here is when we cite the literature, we either cite it directly, meaning I heard about something in a talk or I read it and therefore I cite it, versus I read a paper and it mentions this other paper and I think it's really useful, hopefully I'll read it, but like there is some research that points out that people just cite it without reading, and that's called indirect citations. So Price, in his model of citations, said that citation is based on preferential attachment or cumulative advantage, and he showed that that's true. But he also has this initial condition or the initial uniform probability of, like you have to start the process somehow. And that was uniform probability of 1. And that's your direct citation for him. And indirect is once you start getting cited, then preferential attachment kicks in. And if you use Price's model, it really follows empirical data very well, but not for papers with no citations and not for papers with very large number of citations. I looked at the team size distribution, which follows, like if you look, it looks very similar to the citation distribution. So what I actually then, I added the team size to the play. So the direct citation model is really using the team size to get like how much initial citation you get. And that's again, not because the system is gamed, but if more people worked on a paper, more people are aware of the paper, they are likely to add or use it or expand on it in their different lines of research, even the ones that's not together. Also, they may be talking to their colleagues, so more people could even indirectly or directly from talking to them learn about papers. So it only makes sense that large teams would have larger initial direct citations just because of the nature. Like it's, again, it doesn't have to do anything bad. And if you introduce that, then the direct citation is not uniform. It depends on the team sizes. And then the preferential attachment kicks in. And according to this model, you can see that the distributions we get are fairly correspondent. So like big teams, again, this is not causal by any means, but it does seem that if we think about citation as direct and indirect, team sizes also do matter for the outcomes. And I'm going to skip this large part because I already went over time and close it with this and open up for any questions you may have. Thank you.
Thank you very much, Staša. So anyone who has a question can, excuse me, can raise their hand in Zoom or feel free to type it into the Q&A window also. And maybe, while we're waiting for them, I might start with a question for you. This was a point you went over quickly there, a a little bit in your science as a team effort section, but where is, I kind of agree, just based on my own experience, that there's a difference between big science and largish teams. But where is the crossover? Is there a cognitive limit or something where we can't interact with so many people once the team gets to a certain size? What do you think? How do you distinguish the two?
It's really interesting question. I think that, and I think that there is a limit to the cognitive extent in terms of, and in some of the other research I looked at, and it might have been arbitrary, but the limit for big science versus very large team science was around 20. So you could have up to 20 and it still behaved more or less as larger teams. And then after, like beyond 20, it starts having very, very different dynamics. I think it's driven, and most of the big science research, and I wasn't like, that wasn't my focus. Like I did it for nanoscience, and that was like, I saw that because I was testing for the teams and preferential attachment. And I did see that like kind of border around 20, and like I didn't explore it then further. But the more I read about big science, it's really qualitatively different. In a way, the way these things are formed, they start, and that can go back to the other paper where I do the core and extended teams. But these big teams really start with a number of smaller core teams. So when I showed how LIGO started, there was 3 institutions, but actually there were 3 sets of core teams that joined forces. So there were 3, but actually there were not 3 people. There maybe was around 20 people at that time. And it was still not big science. But once they started adding more, right? The nature, and they piloted things, and they were doing things more at the small science scale level, right? But then once they needed a threshold, and that's the fascinating, like if one reads, there are a number of ethnographies about this research. Once they started growing, like once they did it pilots and tests, and they really started shifting into big science, it became a mess. In terms of people really didn't know how to do big science. A lot of them were theoretical physicists. So they, to kind of save the thing, most of them added either the project manager who had experience with the effort, or they brought in the particle physicist who worked. And there were people who were instrumental early on, but they couldn't shift to big science mode. They left the project. So it's a fascinating story, but it is different. And it's not just the size, it really requires different way of doing things after a while. So hope that answers. It's kind of a longer.
Yeah, it's an interesting, that's a very interesting answer. It seems like it touches on management and getting into management versus science. But let me, maybe we should go to other people's questions. So there's a question from Suzanne Vanderlee. I'll just read it. I wonder if you would elaborate on the tectonic aspects of the shift in science. As you likely know, tectonic plates are large and massive, and they shift very slowly, on the order of millimeters per year, which is also the speed at which fingernails grow. So,
and I would say that everything I've shown, maybe it's not the level of millimeters of nails and stuff, but I've shown you that these things did not come overnight, right? I said that all of these things started being put in motion at least since 1940s, but a lot of the things even before that. So I've said some of the things being seen in the end of the 19th century, early 20th century, really big, although there was a massive shift in terms of how things were done in the 1945. All of the measures we see, they look the same. They were incremental. There wasn't this like, all of a sudden we have different mode, right? Like we changed a little thing and everything looks different. No, everything looks more or less the same. So I think the science is this slow shift. And it did take at least 60 years to really start maybe seeing the interaction. And maybe like, if you now look back to the 40s, it really now looks more significantly different than it did when we introduced a lot of these changes. So that's where I think tectonic shift is more, because although we're introducing these things, the outcomes of these changes is not visible even within the 5 to 10 years, it does take time for these things to propagate and to start seeing shifts. Even interdisciplinarity, so much, like even from 1990s, so much money poured into like starting from nanoscience, like billions at this point poured, and we still have only 10% of paper being interdisciplinary. I would say that's kind of slow. So yeah, maybe not the best one, but I still think it's appropriate because science is slowly changing ship.
Okay, more questions coming in here. So I'll read the next one for you. It's all from Neil Ormos, who asked an earlier question. Given the speaker's strict definition of interdisciplinarity, could the enhanced attrition that you noted at 10 years for highly interdisciplinary investigators be explained by a difference in attention in professional networking within the field versus outside the field? Such as people who devote more attention to networking outside their fields and less within their field, being less successful in tenure and promotion at their institution.
That's a great comment. I think that may be. I mean, we didn't look. I think there are lots of factors, and one would be highly interdisciplinary nature of this research is such that you are right. It does require interaction outside of the field. It also draws, if any of you, and I have collaborated with like now I'm working with economists, I still work with physicists, and it's really interesting also deciding where to publish. So that's how I ended with physics review letters and others. And when you opt for tenure in certain fields, it does matter. Like certain fields have very strict ideas of journals and the types of papers. Like it's almost a cookie cutter. Like you need to look like this, and if you don't look like this, you're at a peril. And you are right. If you engage in this research, you engage with outside of that what others look like. And yes, you would be at a greater peril because your dossier or like your output at the time would look different. Even I've heard recently that somebody was, I'm not sure whether denied tenure, but at least had trouble because I think they were in the management department and they didn't have right publications, although they had PNAS publications in sciences, but that doesn't count. In that world. So yeah, you're right. I think that could be driving as well, like why we are seeing attrition.
Yeah, that relates to a question I had, but I don't want to dominate this. There's another one also from Neil Ormos, but I'm going to leave that for later in the interest of getting more people the opportunity. So here's a question from Mike Rogalski. Is there a way to measure or gauge overall cognitive depth? So something like a companion concept of cognitive extent, where maybe I'll leave it at that. He elaborates, but I'll let you maybe address that first part of it.
I think there is. So I have to say with the cognitive extent, it's a paper that I did a while ago, and I never thought that that's the measure. I just thought I'll give it a try. I think it's a really underutilized way of looking things. And like I came up with that, and I wish more people kind of would work in that. And you're right. I think in order to get a better sense, we would need a complementary thing. It's not only how much, and I kind of hinted at that, right? Because I said, well, they may cover a lot, but maybe they also cover a lot deep-wise, right? It's like, and I think the third area is number of people. So there is this really great book called Academic Tribes and Territories that uses this metaphor of sciences covering different territories. So some are cities, others are villages, and they have different, so cities usually have larger territory than villages, but they also have higher density of population. And I think personally, what I would love to see is complementary measure of that, but also measure of how many people are actually trying to push this forward, and maybe how many, and it goes to the first question, which is, well, how do we know that they're not just solving stuff? So I think there is a room to try and bring all of this together. Like what I presented, like this is by no means an answer. I'm just trying to open, I wish more people would try and look into this with complementary measures.
Also, yeah, very interesting point. From Tomo Bell, here's maybe one last question since we'll have to wrap up. Is that thank you for the amazing talk. One of the challenges I face that it takes so long to publish interdisciplinary papers as an editor, usually has a hard time finding reviewers. Do you have any suggestions to address this common issue? That's certainly something I've run into also.
I have to say,
I'm sure
I run
you
into
have.
that all the time. I
Yeah.
don't, because I think what I do, it falls into that category. And some of the research that I did was, there is this idea that, okay, science, nature, and PNAS, they are different kind, like they have different dynamics. But even if you look at PLOS One, right, or these journals that don't have such a high barrier, but are considered to be multidisciplinary, they're actually not. So you end up with a disciplinary editor who knows particular types of reviewers, and they share it with that. So what these journals do, they are not more interdisciplinary in terms of the individual papers, are not more interdisciplinary than individual papers in monodisciplinary journals. They just tend to publish on a wider range of topics. I don't have a good solution, except that if it's a work, I think what may help is if one knows that there are more people working in the area, just maybe finding, so that's what I did initially. I see where research that's similar to mine got published. So I figured out there might be somebody who could understand like who the potential reviewers are. So I would send to those venues. And if you look, like I published in different venues, but that's what I do. If I know that somebody's doing similar research, which managed to get published, I would target those publications. But it's a great problem, I agree. I don't have a good solution. I get stuff rejected. It's not easy to actually publish stuff when you are in that research with Bruce, we call it falling through cracks. And in a way, interdisciplinarity is in cracks. And like, how can we actually make it out of there? Because it's extremely difficult to do. And although nominally we are all for it, we are not, because it's difficult to publish, it's difficult to get tenure. It's very difficult to actually describe that and get recognition and rewards and continue doing it. So I don't have solutions. I wish I did.
Yeah, I think that's an open problem that is a real serious issue. But anyway, thank you so much for your talk. There are more questions that maybe if maybe you'll be able to take a look at afterwards. I'm not sure if that's
we
possible.
can forward those after the talk. Staša, maybe you would be able to answer our participants directly if that would be okay with you.
Yeah, I'll try to do that. Yeah. And I know I went a bit over, so sorry. But there were so many things that I tried to cover. So.
It was a great talk. Thank you so much, Staša, for giving us your time and all the interesting topics you covered there. So well, thank you again and say goodbye.
Thank you.
Thanks so very much.
Thank you. Bye.
Bye.
Bye.